Hi everyone, this lesson is for Algebra 2 honor students. This is Chapter 12 Probability, Day 1. So a little bit of an introduction to probability as well as going over some fundamental counting principles. So let's get started. Learning targets determine the number of outcomes in an event or sample space, which is the total, without listing or counting them, just trying to find the number of outcomes. So basically probability, number of ways something can happen over the total number of outcomes. And that those outcomes could be your sample space. It's like could be anything, whether you're talking about money or you're talking about dice or you're talking about marbles, etc., or cards even. So event is just a single result of an experiment. And most important is that when you ask a probability of something happening, the probability of something happening has to be in between 0 and 1. Can't be 0, can't be 1, has to be in between 0 and 1. Anything over 1, it's not, you're incorrect. And so just remember that. So we're going to start off with cards. Something about card facts is that how many cards are in a deck? Well, there's 52 cards in a deck. There's 4 suits. Those are the hearts, spades, and clubs, and diamonds. And what did I miss? Hearts, spades, clubs, diamonds. That's it. How many cards are in each suit? There's 13. So there's 13 hearts, 13 clubs, etc. Your face cards are the jacks, queens, and kings. And, of course, you know this, but I mean, it just seems like everybody would know this. But just so you do know, face cards are called face cards because they have a face on them. There's like the king's face, the queen's face, and the jack's face, right? So here's a sample deck. We've got clubs, diamonds, hearts, and spades. What's the probability of drawing, let's say, an ace? So when you're looking at this and you're looking at, all my aces, these are all my aces. So it looks like I have 4 aces, right? So I've got 4 aces out of 52. So 4 out of 52 can reduce to 1 out of 13. So that would be the probability of drawing an ace is 4 out of the total sample space, which is 52 cards. Okay. So then what is the probability of drawing 2 spades? So here are my spades right here. So of those spades, the first, drawing, you're only going to draw 1 card at a time. So you're going to draw a spade, and the probability of that spade is going to be 13 out of 52. And then let's say I put that spade back. And then the probability of drawing another spade would be another 13 out of 52. And in this case, what we're going to have is 169. I think it's 2,704. But realistically, what we're saying is 13 out of 52 is realistically 1/4 times 1/4, which reduces to 1/16. And just to be clear, when you're drawing 2 spades, they didn't really give you any direction as far as, am I putting the card back or am I keeping it? Because if I was keeping that card, when I drew the second card, right, that would be out of 51 because I would have 1 less card to choose from. So here's some practice with cards. And so let's talk about this. What we're looking at is you're playing cards with friends. And as you're playing cards with friends, suppose you draw a card from, again, a normal 52 card deck. What is the probability? So we're asking the probability. So it's not just what are the chances of drawing a red card? The chances of drawing a red card are 26. But if I say, what's the probability of drawing a red card out of all of the cards, that would be 26 out of 52, which because there's half red, half black cards, it's going to be 1 out of 2 or 1/2. Probability again of drawing a spade. Well, there's 13 spades out of 52. And again, that reduces to 1 out of 4. Probability of drawing a 2. There are 4 2s. And so that would be 4 out of 52 or 1 out of 13. Probability of drawing 2 kings. Now, again, very similar to the spades, but in this case, I'm drawing 4. So the probability of drawing a king is going to be 4 out of 52. But if I keep that card, right, and if I keep that card and I don't put it back, the next draw that I make is 3 out of 51. So that ends up being, I think it's out of 1 out of 221. I think that ends up to be the reduced value. For letter E, a jack and then an ace. So the probability of drawing a jack, again, that's 4 out of 52 because there's 4 jacks out of the deck. And then an ace. So, and then again, times. And then, that means times. And then an ace. And an ace, again, is 4 out of 52 if I replace that card. So I've got 4 chances to get a jack. 4 out of 52. I'm going to put that back. And then getting an ace. Then I'm going to have 4 out of 52. And so that would be 1 out of, I think it's 169 is that value. So I think for me, you definitely, when you're doing these, you do need to know, am I replacing the card or am I not replacing the card? Because, for example, with the 2 kings, if I, like in this case, I kept the card for this problem, and here I replaced the card. So each one is going to give me a different outcome, because if I had not kept this card and I plugged it back in, right, I would still have 52 cards to choose from. The probability of tossing a coin. So now I love this problem. You want to toss a coin, and when you're tossing a coin, you have to ask yourself, how many times am I tossing this coin, right? Most often when it just says, hey, I'm going to flip the coin, what's the probability of, flipping a coin? You've got heads or tails, right? So you've got the first option when you toss a coin is you have heads or tails. And so this says draw a tree diagram, because what's happening is you start your diagram, you're saying, hey, I could get heads or I could get tails. And so I'm going to split this up a little bit for this time. So we've got heads here and then we have tails. But then that's my first toss. So that's my first toss. And so the second toss, again, if I had had heads the first time, the next time I could have gotten heads or tails again. Likewise, if I had gotten tails the first time, the second time I could have gotten, again, heads or tails, because each time I toss the coin, it's a 50-50 chance. Now, that's my second toss. Now on my third toss, which is what it looks like we're doing, is a 3-toss thing here. I could have, for the heads, I could have again, heads or tails. On the third toss here, my outcomes would have been heads or tails also. For this one, tails first, then heads, also, again, heads or tails. And then lastly, if I had gotten tails the first time, tails the second toss, third toss, I could, again, heads or tails. So listing all of my outcomes is something that I recommend for sure. You guys, because it's one thing to draw the tree diagram, but it's another thing to say, well, I have a tree diagram, but what does that mean? It means that the first toss I got heads, heads, heads. So that's an option, heads and then heads and then heads. And I could have gotten heads, heads, tails. So that's heads, heads, tails. Heads, tails, heads. So you want to label all of these options that you have. So heads, tails, tails. And then I then have on this part here, I've got a tails, heads, heads. I've got tails, heads, tails. I've got tails, tails, heads, and then lastly I have tails, tails, tails. Now, once I've done this, and this should say tossing a coin, this should say 3 times. What is the probability of getting 3 tails? Well, the probability of getting 3 tails, looks like I have 4 outcomes here, 4 outcomes here. That makes a total of 8 outcomes. So when they're asking for this value P, which is the way you would write a probability problem, the probability of getting 3 tails would be the probability of getting, let's see, all 3 tails would be this one right here. So 1 out of 8 chances. The probability of getting just 1 tail. So I'm looking through, I've got a 1 tail here. That's 2. 1 tail here. And Did I miss one? Yep, I did. And one tail here. So that's 3 out of 8. Now, that would be different, right, if I had said at least 3 tails, because that would have meant I could have had at least one tail, because I could have had one tail, 2 tails, or 3 tails. So be careful on the wording with that. Exactly 2 tails. Well, that's just exactly the same thing, right? Exactly 2 tails. Let's see. We've got one here, 2 tails. We have 2 tails. We have 2 tails. Also 3 out of 8. The probability of getting no tails, well, if I don't have any tails, then I have all heads. And the probability of that is just 1 out of 8. Now, the last part says the probability of getting at least 2 tails. So that means I could get 2 tails or more. So, or more would mean 3. So 2 or 3 tails. So we already know that the probability of getting 2 tails is 3 out of 8. So is there, and then the only other option is to have 3 tails, which is one possibility for that. So then it's 3/8 plus one option is another 1/8. So that's 3/8 plus 1/8, which is 4/8, or half, 50% chance of getting at least 2 tails. Okay, these are fun. All right, the next problems here are like this. They're saying, hey, we've got the deck of cards. Find the probability. So again, they want everything out of sample space. The probability of getting 2 hearts. Now these problems here are more detailed, more specific. Are we replacing it? Are we not replacing it? So the probability of getting 2 hearts when the first card is replaced. So the first heart is 13 out of 52. And then, and means multiply in probability land. So 13 out of 52. And then I'm replacing that again. So that's, now I've got a full deck again. So it's 13 out of 52. So total, what is that? 1/4 times 1/4, which is 1/16. Okay, and then here's a little explanation too, if you need a little bit extra help on that. B, selecting 2 hearts when the first card is not replaced. So the first option is 13 out of 52. But then if I don't replace the card, right, so now instead of the heart, I took a heart out and I took a card out. So now that's going to be possibility of 12 out of 51. That reduces also to 1 out of 17. And then you guys would be able to, again, you know, there's just fewer cards to choose from. You know, it definitely affects the selection and the probability for the next value that you're drawing. A queen is drawn. So how many queens are there in a deck? There's 4 out of 52. I don't replace it. So now I have that. But I'm not taking another queen, because if I took another queen, that would be 3. But I'm not taking a queen. I'm now taking a king. So if the probability of taking a king is 4, but not out of 52 because I took a card out. So now that's out of 51. So 4 out of 51, that reduces to that. All right, there we go. Okay. Now let's switch to a bag of beads. We have 2 black ones, 3 whites, 5 reds. So that's 5, 6, 7, 8, 9, 10. So we got a total of 10 beads. A bead is selected at random. So you take out a bead. Determine whether the events are independent or dependent. Find the indicated probability. So does it affect, is it like dependent on something else, or is it independent, meaning it's just, you know, only affecting itself? Does it affect something else, or does it not? Selecting a white bead. So a white bead, I've got 3 white beads. So selecting a white bead, so that's 3 out of 10. And then, see this and then? That means times. So and then selecting a red bead. A red bead is 5 out of 10. So this makes 15 out of 100, and you guys can reduce that. The next yep, there we go. Next problem. Selecting a white bead. So actually, I'm going to go back and just try to remember. I've got 2 black, 3 white, 5 red. So 2 black, 5 red, and I think I said 3 white. Yep, 3 white. So here we go. Selecting a white bead. So I'm going to select a white bead, 3. So I've got 3 out of 10. And then, not replacing it. So now I have 1 less bead. So I don't replace it. And then selecting a red bead. So now I've got 5 out of 1 less than 10 because I didn't replace it. So now that's out of 9. 15 out of 90, 1 out of 6. There we go. Selecting 3 non-red beads. So again, we had 2 black, 3 white. So we had 2 black, we had 3 white, and then we had 5 red. So selecting 3 non-red beads without replacement. So the first option, right, is, what's my first option? My first option is getting, I think, what is that? 5 out of 10, because that's non-red, right? So 5 out of 10. And then my second option for this, if I'm selecting, let's see, not replacement, the next one is going to be 5 out of 9, right? And then that is just not replacing it and then selecting without replacement. Hold on, I'm just confusing myself. Give me a second. Okay, so hello. After you select a red bead, right, you have 1 less bead. So obviously that should have been 4. I know you're probably screaming at the video. Okay. So then the third time is 3 out of 8, because again, we have 1 less bead. So I don't know what that is, 60 over 720. So reduce that. And then let's see, what does this say? Pretty much the same thing. Non-red, 1, the first one was non-red. Yeah. And you just go 1 down each time. So, all right. So switching to, away from beads, away from cards, we're going to switch to, suppose that we have 4 random people are selected from a group. Now, think about it like this. We have 2 freshmen and 2 sophomores. We've got 4 people are selected. We want 2 freshmen. We want 2 sophomores. But out of the whole group, we have 4 freshmen and we have 6 sophomores. So if I want 2 freshmen, then, and I want 4 people total, right? So I want 2 freshmen, but that's 2 out of 4. So that's 2 out of 4 freshmen. And then again, which is the times, I'm going to choose sophomores. So that's 2 out of 6. So that, and then I'm going to go 2 out of 6. And so that's just 4 out of 24, which is 1 out of 6. Okay. What is the probability that I get 1 freshman and 3 sophomores? So again, I'm going to select 1 freshman, and then that's 1 out of 4. And then I have 3 sophomores, so that's 3 out of 6. So the total probability for this would be 3 out of 24, which is just 1 out of 8. All right, so yeah, I did that. That is super cool, I know. The act of rolling the dice is called a random experiment, okay? So the word random basically lets you know that there is no way of telling beforehand what's going to happen or how the roll is going to come out. Because each time I do this, I'm going to get a new value. Now, depends on how many dice I'm rolling, right? Am I rolling 1 dice or more than one, more than 1 dice or die? But also, are they the same color? Is that going to make any difference? But each way that the dice come up and you're out is called an outcome. So outcomes are all equally likely depending on, as a result of the experiment. So for this right here, what you guys are looking at is rolling a pair of dice. Now, right here, I have white dice and I have black dice. Okay. So if you think about it, you could have 1 white, 1 black dice. You could have, a 2 and so there's all different kinds of possibilities. So depending on, what they're asking you to find is going to change the outcome. So for example, there's 36 different possibilities when you think about it, right? Of all the different things that you have. But if I just roll 1 dice, right? That's just 1 out of 6 chances of getting a number. So thinking about that, when you're rolling a pair of dice, this just sort of ups the ante. It's a little bit different. So if you want a total of 10, then you're thinking, what are all the ways that I can make a total of 10? And that's like completely 5 and 5 is 1. And that's not going to matter because it's going to be a red and black or a white and black no matter what. So that's one option. I could have a 4 and a 6, right? And I could have a 6 and a 4 combination. So, and that's it actually. I've got a 4 and a 6 and a 4, and then I've got the 5 and the 5. And the 4 and the 6, this is a white 4, black 6, or a white 6 and a black 4. So those right there, because I can flip the values, that's 3 different options, right? So that's 3 out of 36, which is the probability is going to be 1 out of 12. The sum of at least 10. Now, that's a little bit tricky because they're saying, I want a sum of 10 or more. And if I do 10 or more, right, I'm going to start with my 3 out of 36, of course. But then or more means I could have an 11, I could have a 12. So what are my options for 11? It's a black 6 and a white 5, or a black 5 and a white 6. So that's 2 more. And then I could get a 6 and a 6. That's going to make 12. And so that's another 3 opportunities. So that's going to make 3 out of 36 plus another 3 chances. And that's going to be 6 out of 36, which, so the sum of getting at least a 10 is going to be, 6 out of 36. So that's 1 out of 6. And then to get a sum less than 10, right? Think about it. If you have a sum more than 10, or at least 10 or more, that's 6. So then all the rest of them, which is less, would be 30 out of 36. And so reducing by 6 would give me 5 out of 6. So 5 out of 6 chances. So probability of our independent events, right? The events are independent. You've got one effect does not affect the other. So basically you're saying these are independent of each other. Okay, so the probability of rolling a 6 on one of the values is 1/6. And then a 6 on the other value is also 1 out of 6. So that just makes 1 out of 36 chances. And so that's how you would show an independent event. Each one of these events is separate. Dependent events are going to depend on, what's happening and how you are, depending on if it's with replacement or without replacement, of course. But dependent events affect something that, the next event, the next value. So if I have 2 lemons and a lime, so that's 3 things in the bag. What is the probability of drawing 2 lemons? Well, the first option is 2 out of 3. All right. So I drew 2 out of 3. I have a 2 chance because I have 2 lemons. Now, if I don't replace that, this is without replacement. These are, this is going to depend on the next value. So it's, without replacement, my next option is now I have 1 less, value, and I have possibility of 1 less lemon. So now my next probability is 1 out of 2. And so that's going to be 2 out of 6. And so that's going to be 1 out of 6. So this just kind of gives you a tree diagram to help you. But basically, when things are dependent, the occurrence of one event depends on the probability of the next event happening. So it's going to change it. So lastly, counting principles. And counting principles are kind of cool, actually, because what we're talking about is something called the fundamental counting principle, which is basically 2 options. You've got your and then, which is what we've been doing this entire time with probability. And when you see and, I know and you think of plus, but it's not in probability language here. And then is a times. But when they're saying or means add. So they're asking you to add the 2 different probabilities. Okay. So that being said, we have something called the fundamental counting principle. And this basically says if there's m ways of doing something and there's n ways of doing something else, then there are m times n ways of doing both. Okay, so you can actually accomplish two tasks this way. So how many different top and pants outfits could you make if you had 4 tops and 2 pair of pants? So think about it like this. You're not going to wear a top or a pair of pants, right? You're going to wear a top, you're going to select a top, and then you're going to select a pair of pants. Now, of course, you could wear Spider-Man red here with these pants, and then this one with this one. You could wear this top with this and with that. You could wear this top, Hulk, with blue or with purple, or you could wear this Avengers shirt with blue and then purple. So like, how many ways is that? Well, an easier way of finding that, other than just making little lines and diagrams and stuff like that, is just say, well, I've got 4 tops I'm going to choose from, and then I have 2 pair of pants that I can choose from. So how many different combinations? I'm not asking for the probability. I'm asking for how many combinations can I have all together? Well, I can have 8. 4 times 2. So just basically fundamental counting principle just says, you could have more than 2 groups. For example, you could have not just 4 tops and 2 pair of jeans. You could have 2 pair of jeans. You could have 3 t-shirts, and you can have 2 pairs of sneakers. How many different combinations can you come up with these 3? And that's just 2 times 3 times 2, which is going to be 12. Okay. So this is a really, iconic one, which is just 31 flavors. Actually, I used to work there. Fun fact. And for this right here, it says you've got 31 flavors, and you've got 3 different types of cones, although I'm sure nowadays they have way more than that. How many different possibilities could we come up with, right? So we have 31 flavors I can choose from, and then I'm going to have 3 types of cones. Now, if you want a cone and an ice cream, because of course I could have just a cone, if some people like to eat just the cones, or I could have just the ice cream, and I could do either or. But most people, if you get an ice cream, you're going to need a cone with that, right? So that would just be 93 different ice cream cones that you could make with this option. Okay. Fundamental counting theorem is pretty basic. We've got how many sandwiches can you make? So this is one of my favorite places to go for sandwiches. It's in Los Angeles. It's called Eastside Market. And as you can see, this has been out for a very, very long time. A deli, we're going to call this the Eastside Market Deli, has 9 types of meat, 12 types of cheese, 5 types of bread. How many different sandwiches can you make if you just choose 1 type of meat, 1 type of cheese, and then 1 type of bread? Well, we've got 9 types of meat we can choose from. So we're going to choose a meat, and then we're going to choose, we have 12 types of cheese. So then we have 12 options for cheese. And then we have, what do we have? 1 type of cheese, and 5 types of bread. So we're just going to multiply 9 times 12 times 5. We get 540, not 200. We get 540 different types of sandwich that the Eastside Market can make just based on their really awesome selection of meats, breads, and cheeses. So this is just a screen that show you sort of a layout, sort of flow chart, that if you went to another establishment, another deli, we have ham, turkey, roast beef, pastrami. That's 4 different types of sandwiches, or 4 different types of meats. And then you could just have the different types of bread. So this is saying we've got 4 meats here, and then we have 3 breads, and then they didn't put anything else in that, so no cheese. But that's just then 4 times 3, which gives you 12 options. So the more condiments that you add, the more, obviously, the more options that you're going to have at the end to, have a selection. This police use photographs of various facial features to help witnesses identify suspects. One basic identification kit contains 195 hairlines, 99 eyes and eyebrows, so those are together, 89 noses, 105 mouths, and 74 chins and cheeks. So thinking about all the different faces and identifications that our kit can have and produce, how many different people, that you just multiply all of those out. You've got all, 1 times hairlines times eyes times noses times mouths and chins, etc., and multiply all that out, and that's going to give you the most accurate value. Okay. Sam visits the pet store. There's 37 dogs and cats. So in this problem here, just basically I want a dog or a cat. So I've got 37 dogs, I've got 15 cats. I want a dog or a cat. So I've got 37 plus 15. And so what is that, 52? And so I've got 52 options of getting a dog or a cat. But if I want a dog and a cat, I have a lot more options. I could have 37 dogs, and then I can have 15 different types of cats. And so what they're asking you is like, basically, how many different ways can you select this? I could have this dog with that cat, or that dog with the second cat, that dog with the third cat, etc. And so there's so many different, ways that you can combine those. There's actually 555 ways of doing that. Reading list has 11 novels and 5 mysteries. And how many different ways can you select a novel or a mystery? So I've got 11 novels, or means add, so add 5. So that's going to be 16 ways I could select them. A novel and then a mystery. So again, 11 times 5, which is just 55. A mystery and then another mystery. Well, that one could be a little bit tricky because I've got a mystery. I've got 5 mysteries, but I picked one. But then my next chance is going to be 4 because I already took a mystery out. So my different ways I could select that is now 20 because of course I selected 1. Okay. This is a great question. We've got baseball teams, and 9 people are on a baseball team, and we're trying to decide who's going to play what position. Now, how many different ways out of 9 people on a baseball team, how many different ways can I select the person to be a pitcher? Well, there's 9. Okay. 9 different people, 9 ways. But if you think about it, how many different, after someone has already been selected as a pitcher, how many different ways could they select someone else to be the catcher? So when you think about that, you've already given up 1 person. So now you have just 8 people left because you picked 1. But if I want to be able to select a pitcher and then a catcher, now I have to multiply. I got a pitcher. I got 9 people I could pick for the pitcher. And then the second option is going to be, I have 8 choices now. So that's just 72. After the pitcher and the catcher have been selected, in how many ways can I select select a first baseman? Just 7. In how many ways could they select a pitcher, a catcher, and then a first baseman? So 9 and then 8, and then 9, 8, and then 7. And I don't know, what is that, 504? Okay, now the last question is probably what you thought the first question would be, but it's not. Okay, I want to know in how many different ways could I fill all 9 positions? Well, that's 9 factorial, because I could pick 9 people. I have choices of 9 people the first time, 8 people, then 7, and then 6, and then 5 options, and then 4, and then 3, and then 2, and then 1. So be careful the way that the question is worded. If you just want to know how many different ways I could select a person out of 9. There's just 9 people to choose from. But if I want to know how many different ways can I select for every single position to be filled, I've got 9 options the first time, which is what they asked me in the first question. But the second time, I now have 8, which is what they asked me here. The third option, I only have 7, which is what they asked me here. But then to fill all the rest of the positions, right, I have 6 times 5 times 4 times 3 times 2 times 1. So for this one right here, we're talking about license plates. And this is a really great question, actually, because this is what every state goes through. And so in this case, in this state, we're going to assume we have 6 characters in our license plate, right? That means that you would have, we've got 1, 2, 3, 4, 5, 6 characters. Some of the states use 2 letters, okay, and a number from 1 to 999. So meaning this would be a letter, and then I'd have a number, and number. So the most number, right, that would be, the most value for that would be up to, actually, that would be 9,999. But then other license plates, right, another option, 1, 2, 3, 4, 5, 6, has 3 letters. So it would be like letter, and then number. So for this one right here, we have 9,999 options. But for this one, I only have 999 options for my numbers, okay? And the letters, of course, are 26 letters in the alphabet. So we got 26 each time. Unless, now think about it like that too, is that unless one of the numbers, let's say they make a rule, which they didn't, but they make a rule where you can't use the same letter twice. That would change it. But okay, so if I want to know what the probability is, which one has more, not probability. I just want to know which one has more options. Is it this one or this one? Well, it turns out that, let's see, for the first one, if I want to find the number of 2 letters and 4 numbers, right? That's going to be 2 letters. So 26 times 26 times 9,999 numbers, right? The second one is going to be the number of 3 letters and 3 numbers. And so that would be 26 times 26 times 26, and then times 999. So for these problems here, it turns out when you multiply these, you need to multiply these out. I think this one down here, this value, when it all said and done, you guys can multiply that out, turns out to be about 10, I want to say maybe 10 million more. This number is so much larger here than this one. So it's about 10 million more. Okay. How many license plates could there be using either 2 letters and 4 digits? So now we're talking about digits. Or, hold on a second. How many license plates can there be either using 2 letters and 4 digits, which is this, or 3 letters and 3 digits? So now they're asking me not to do this and then this. They're asking me to do or, which basically means I need to add my 2 sums up, which was like 6,759. Oh, actually it wasn't 10 million, was it? 324. And then I think the other value was like 17,558 for something. I don't remember those last 2 numbers. And then I think the sum is 24,317,748. Okay. So that's how many plates that we could be all together. So is that worth it? Do I have 24 million plates that I need, or do I need more or less, etc.? So when you're looking at that, you're thinking, well, there are about 100 million motor vehicles in the United States. So would it be possible to have this national license plate program in our system? I would definitely not, right? Because if we have 100 million motor vehicles, at least, and we only have the option for 24 million license plates, that's a big deal, right? So that's a huge deal. And so that would be a definite no. We need a different plate. We need a different option because our state would not, this would not work for our state. Okay. All right. So I think that's kind of cool. Last thoughts. Powerball, of course. To win the Powerball, the number on your ticket must match the number of balls chosen from a bin of 59 numbers. The number of the Powerball, which is chosen from a bin of 35 numbers. What are the odds that you're going to win big, retire young, and split the winnings with your, favorite Algebra 2 honors teacher, right? Wonder what those odds are. Let me know. Learning targets, I believe we've hit those. So sample space, outcomes. You should definitely read the textbook for this since this is an asynchronous day. 300, it starts with 632. There's 3 parts to this. There's probability using cards. There's probability, and then there's fundamental counting theorem. So these are the different parts. Wishing you good luck. See you on Thursday. Thanks for watching.